The problem 2 on homework 1, where we have this system of differential equations and we have this parameter a real number. We're going to use separation of variables to get the solutions for the solutions, solve for the solutions x of t and y of t. We'll solve in the y direction. So we have y prime, which is dy dt, equals ay. We divide y, get 1 over y, multiply up dt and integrate. We get log of an absolute value of y equals at plus c. Uh, both sides, exponentiate both sides, we get absolute value y is equal to uh, e to the at c. We use exponent properties to split it like this. We drop the absolute values, creating an arbitrary constant with a certain sign, the desired sign. And we call this constant y naught. We do the same thing in the x direction, but with 2 instead of arbitrary a. We sketch the phase planes, phase portraits for these values a, negative 1, 0, 1, 2. And yes, don't use technology for this. You can draw this by hand. I use Tick Picture in LaTeX, just putting values of t into these solutions for arbitrary, for well chosen initial conditions so that the picture stays, so that the function stays on the page. And you can see that if uh, a is negative, these two have different sign, and that will give us a saddle. And if a is positive, we will have unstable nodes. Our null clines are the x-axis, the y-axis. When a is equal to 0, every y value is a null cline in the x direction, in the y direction, and x equals 0 for the x equals 0 for the x direction. There is no movement in the x direction. But also there's no movement in the y direction because a is 0. So the y-axis is the stable axis. For a equals positive 1, we get a starburst. Equilibrium point is 0, 0 in all these cases. And the null clines are this x and y axis for C and D, so to speak. We use Mathematic or Python. I use Python. We get our phase portraits. We use these vector fields to classify our equilibrium points. And we have an equilibrium at 0, 0, 0, 0, 0, 0, and this whole axis is an equilibrium axis. Later on in the course, we learn about setting up a constant coefficient matrix for systems of linear differential equations. We see that the trace is 2 plus a, and the determinant is 2 times a minus 0 times 0, so 2a. And in the trace determinant plane, there's this parabola, which is traced out by the trace squared over 4, which corresponds to the discriminant in the quadratic formula, which tells us whether our eigenvalues of this matrix are real or complex. You go into Python. Do I have it? Doesn't really matter. Well, I may not have done it today, but you plug in these values for A, you run it through these formulas, and it gives you the trace, the determinant, the value of the parabola at that point. So trace squared over 4 is a quarter. Yeah. And we see that the trace determinant plane, because the determinant is always negative for values less than a values less than 0, is down here. I'm trying to keep this video in under 7 minutes, so I'm going pretty fast. Um, For a equal to 0, we get points, so the determinant is 0. 2 times 0 is 0. We get points, non-isolated fixed points along this axis, which corresponds to our entire y-axis being a fixed point. So non-isolated fixed points. For a equals 1, we get an unstable node. We have the trace of 3, which is out here, and a determinant of 2, which is below the trace determinant parabola. This parabola, trace squared over 4. So it gives us an unstable node. When a is 2, we're on the parabola. We don't know what it is exactly, but looking at the phase portrait, we see that it is a star. And for every other value, it will never reach the trace squared over 4. I don't want to show that. Yes, that concludes this video.